don't have enough label data, like in the case of criminal record, we need a different tool, like the one that can exploit its connection with unlabeled data for label propagation and try to enlarge the training set in some way or the other. This kind of learning is called semi-supervised learning. It's as simple as heat equations. Let's say we have billions of unlabeled nodes in a multiverse, but there are only a few tiny specks of nodes identified as criminals or drug suppliers. So here, we wish to know who might be involved. We want to learn a function that maps the feature vector of minuscule criminals to appropriate labels. If we had information about all the nodes, we could have trained a CNN. And in the case of no info, we could have used clustering. But this case is special because we have some labeled nodes and many unlabeled nodes. Can we somehow exploit this fact? Think of each label as fire burning with intensity equal to label value. The neighboring unlabeled node gets the label value based on how far they are. Too far? No light. Too close? Lit as This is expressed in terms of heat equation, where the values are fixed for the light source or labeled data, and an approximate label values are extrapolated for unlabeled nodes in order to learn the mapping function. That's why it is called semi-supervised learning. Before we go into the complexity of learning a knowledge graph, let's restrict ourselves to learning an undirected graph. You might have heard about convolutional neural network for 1D or 2D data. But have you thought of convolution for graphical data? We'll be now learning graph convolutional networks. It's like a CNN, but for a fixed graph network. It's another interesting way of predicting the same old labels, like are you an undercover agent or are you from Illuminati? Graham Gensel gives a beautiful example of finding users who can be trustworthy for loans in case of money laundering ring. So if we have past graphs of money laundering, we can leverage it to learn the risk factor based on input feature vectors of each node. Without further ado, let's jump into the theory. Let's say that each node I has a d-dimensional descriptor xi to form a feature matrix X, which has dimension n cross d. This means that the features are stacked up like a cake. It can be credit score, gender, etc. Now if we left multiply this feature matrix with an adjacency matrix, then we are basically doing weighted sum of features of neighboring nodes. Whenever you hear the term weighted average, it should trigger the word convolution. Here, if we right multiply a weight vector to the normalized A times F, then it is like combining features of single node differently. By squeezing the matrix vertically, we get the weighted sum of internal node features, creating a column vector corresponding to each node. So for example, if the row vector is credit score is equal to 0.7, gender is equal to 1, then we are just combining these two for each node. And by the way, that's what is spectral graph convolution. If we were to draw parallels between CNN and spectral graph convolution networks, then CNNs, cascaded convolutions, spectral GCN, cascaded spectral graph convolutions, CNNs, labels, spectral GCN, node labels, CNNs, depth is equal to number of filters in previous layer, spectral GCN, depth is equal to number of columns in the weight matrix of previous layer. In short, if we stack up the graph operations just like we do in CNNs, then that's all it takes to build a graph convolution network. It's just that the weights are applied differently followed by an activation. We also have an additional overhead of multiplying the adjacency matrix to selectively take the neighboring nodes into account. Awesome! You just learned graph convolution networks. But wait, all these graphs are undirected, with no given to the type of edge used. A murdered B is same as A loved B. GCN is blind to this. But if we scrape data from web, doesn't it have meaningful edges? And that's where knowledge graphs comes into the picture. A knowledge graph is a directed graph with an edge as a relation. An edge is no longer neutral. DBpedia is one such knowledge graph corresponding to Wikipedia texts. These massive knowledge graphs are defined by schema or metadata called ontology. So if ontology is person is friend of person, the graph can have thousands of nodes for this small piece of metadata. Like John is friend of Khaleesi, and Khaleesi is friend of Tyrion, and Tyrion is friend of Lord Varys. Now if we just add one more triplet to the ontology, namely person is enemy of person, then a whole host of new nodes and relationships come into the knowledge graph. Like Cersei is enemy of Khaleesi, Cersei is enemy of Jon Snow, White Walker is enemy of everyone else. In ontology, we can also mention properties of the relation such as inverse, transitivity, commutativity, and so on. So if A is doctor of B, then the inverse relationship is B is patient of A. Let's imagine a space of entities where the similar entities are closer in space. So if Eminem is a feature vector 10, 15, 3, then the vector assigned to Linkin Park should also be close to 10, 15, 3. This brings us to a fundamental problem, that is embedding relationships and entities. If you have ever tried deep learning models for natural language processing, then this would have been the first thing that anyone would teach. But here, for knowledge graphs, we want one more condition. The embedding of relationship should be approximately equal to the difference between connecting entity vectors. Or in other words, the relationship should shift the entity representation accordingly. For example, Barack plus husband of should give you Michelle. Barack plus was president of should give you USA. Barack plus graduated from should give you Columbia University. So relation embedding should learn these tricky jumps. Just a quick reminder, a GCN is different because it would consider all these relationships as same. What we just studied is nothing but Tran-E embedding approach given by Boris et al. In 2013. The objective function for the same is given by the following equation. Now as you can see that we want to minimize the distance between head plus label and tail, subject plus predicate and object embedding. But there's a fear that all the embedding may become zero vector, because zero vector plus zero vector is always a zero vector. Duh. It satisfies all the constraints, and therefore we need negative samples and mild alteration in objective function. We construct the negative pairs by sampling from some random entities as head or tail. Most likely they are not connected via the relation, and hence we try to increase the distance for this triplet translation. The gamma that you see here is a margin parameter, so that the maximum distance for unrelated pair is regulated. We just try to minimize this overall energy. So now, by this Tran-E model, we can now find cool embedding such that relation-based vector arithmetics can be performed. You can now add a relation. But here's a catch. For relationships like worked in, there can be multiple outgoing connections. It can be home, company, small group, anything. It is impossible to add a vector to an entity and get multiple results. This problem is resolved by Trans-T embedding given by Golong et al. The idea is simple. Let the relationship lie on a different plane that is projected such that this one-to-many problem is taken care of. A plane of relationships is where many entities lie close by, even though their meanings are different. For all this to happen, we assign two vectors to an entity and relation, one for the meaning and other one for creating projection kind of matrix. The matrix constructed by outer product of the projection vector of entities and relation is used to dive into the relationship space. Now the operations similar to Trans-E are performed on the projected space. Bring the head plus label close to the tail on this projected space. Another example can be relationship loves. Entities like cat, dog, human, instrument, mother may be conditionally close in the projected space for relation love. But the conditional projection of these entities will be far away in case of is engaged to. Despite these approaches, there are a lot of areas which are unexplored in knowledge graph. For example, a recent paper titled KB GANs talks about intelligently constructing negative triplets based on adversarial objective. For newbies, you can watch my previous video on GANs. The links are in the description. Anyways, the generator constructs the super cool negative triplet to trick the discriminator function to think that it's a real triplet of subject predicate object. And the discriminator is supposed to be smarter every time by these difficult triplets. Similar ideas have also been used into question answering, where the generator is learning how to break the chatbot by asking god-level questions. The generator is becoming like a parasite which thrives on the loopholes of discriminator. I will have another video for the same, but I hope that you appreciate these open-ended questions which are emerging in the field of knowledge graphs and NLP. I'd like to thank the reviewers for having the patience to read the lengthy script. Now please contribute to the initiative by donating to us via Patreon, because we need the money to scale up the efforts and bring creative weirdos and nerdy dreamers together. Even something as small as $1 per creation can make a collective difference. And if you are even more enthusiastic about contributing, then you can join us on Slack. If you are a good writer, you can share your transcript or blog and we can make a video out of it. And don't forget to subscribe the channel and press the bell icon to never miss an update from Crazy Muse.